Morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. Today's topic falls under the category of options in that there's a lot of second-order effects of some of the changes that took place in the IEEE model, and as people are becoming more experienced with the purpose of doing an arc flash study, there are a lot of questions that kind of arise that kind of affect the scope of work and the cost to the client. And some of this hinges on the fact that there's no longer a low voltage exception. So that's why, and the topic comes up frequently, and that's why I've included it as one of our Tuesday refresher objects or subjects. And as we are in the habit of doing, I'd like to run a couple poll questions just to get some feedback and see how things are perceived in the audience. The first question is, how often have your past projects relied on the low voltage exception for systems less than 240 volts? Again, there's no right or wrong answer. It's strictly just your experience that I'm looking to understand, and perhaps your perspective on the topic. So no liability or obligation, strictly just trying to communicate a little bit in advance of the presentation. All right, let's give this another 5 seconds. Looks like we have close to a quorum. All right, thank you. So here's how folks have weighed in on this topic. Pretty much what I would expect based upon the interest that this subject suggests. Then the second question is, have you or do you use the 2-second rule to minimize instant energy calculations? Well, this is a slightly off topic, off the subject that I was discussing, but it comes into play when we're talking about these changes. And some of it is a little bit alarming to me, the way that people have interpreted what's regarded as the 2-second rule, in spite of the fact that everyone understood it really wasn't a rule. So more on that in a little bit. So if you would please, if you haven't fed into our little survey, please participate. Okay, it looks like we're close to a quorum. Here's how folks have weighed in on this. And good distribution. And this is really where I want to talk as far as the details on this. So very good feedback. And then finally, in your experience, how often does the scope of an arc flash study include single phase loads? And again, this is falls into the category of what's going to happen in the future and how people are anticipating or preparing for it, or kind of the value of conducting a study altogether. So a lot of this, there's not nearly an up or down, yes or no response. Depends upon who you're talking to at the client level. All right, we got a quorum. Here's how folks have weighed in on this. So fair amount of split there. Good. So as you would expect, my intent is to provide some thought into what the possibilities are when you engage a client and you talk about things such as the cost of the study and how this subject of low voltage may or may not impact what his particular needs are, what their needs are. And then a little bit more in depth about this 2-second rule, at least from my perspective. So jump in if you've got questions and we'll see if we can talk about it together. Okay, for those of you that don't know, in the original version of the 1584 standard in 2002, there was a paragraph, if you will, that suggested equipment below 240 volts need not be considered unless it involves at least one 125 kVA or larger transformer in its immediate power supply. And what this resulted in was a license to basically ignore low voltage panels below 240 volts. And it allowed us to minimize the data collection at the very least. And it turns out in the subsequent testing, system testing that IEEE conducted, and other studies that were conducted by individuals and certain companies, it became clear that this wasn't in fact true. There were some loads that could have an arc flash hazard associated in this lower voltage category. So with the release of the 2018 version of 1584, they no longer have this low voltage exception. What they have in place is a statement, this is under chapter 4.3, and it suggests that sustainable arcs are possible but less likely in three-phase operating systems at 240 volts nominal or less with an available short circuit current of less than 2000 amps. And even this is conservative, but what it does is now include the possibility that many of these low voltage panels, 240 volts or less, may need to be included in the study. And I say that because, again, these are all consensus standards, and what works for one client or one company may not necessarily work for another company. And so what I'm thinking, or what I'm suggesting is considering what is important to the client. For instance, there has been a history in arc flash compliance, if you will, in the direction of NFPA 70E and even in this standard 1584, that there's a migration path that has caused a lot of consternation with the changes from one revision to the next. And that requires a fair amount of investment trying to keep up with it. And what IEEE 1584 committee says that they're gearing up for or expecting for the next revision is the potential for a single phase model and a DC model, neither one of which are included currently in the standard. Now, even though the current scope of 1584 is 208 volts through 15,000 volts, there is some acknowledgement that the data matching for the model below 240 volts is not quite as strong as the higher end of the voltage spectrum. And so there's some wiggle room, if you will, and that's by evidence of that low voltage discussion I just had in the previous slide. The fact that the low voltage exception now has been removed, does the client would benefit from including all these panels that were ignored the first time through, and what's the cost impact of a renewal or an update of his previous study? And then how much will it really change the results of the overall system analysis? For instance, does it help to ignore voltage of 240 volts or less if the fault current is less than 2000 amps, which was the cutoff point for the discussion about including low voltage analysis? Again, these are discussion points that I would suggest impact the cost of the study that I'm about to do, and it also be somewhat gauged by the client's need to either maintain compliance, achieve compliance, whether or not the method that's prescribed in 1584 and NFPA 70E fits the needs of his particular business or operation. Again, because there's a consensus standard involved, and if I have a better way of addressing the hazards that affect my employees and I document it, then there's reasons to believe that that would be acceptable as far as an OSHA criteria. Without going down that rabbit hole, let me kind of back up from this list and get into the discussion about the 2-second rule. Now, I put in parentheses or put in quotes the 2-second rule designation because in the original version of 2002, the discussion about a 2-second time limit was in an annex and not technically part of the standard. And they refer to that as informational annexes, and there's a lot of information even in today's release. But it states now in the body of the standard, it's chapter 6.91, discussion of arc duration. If the total protective device clearing time is longer than 2 seconds, consider how long a person is likely to remain in the location of an arc flash. If it's likely that a person exposed to arc flash will move away quickly as possible, and 2 seconds is usually a reasonable assumption for the arc duration to be determined to use to determine the incident energy. In other words, what they're suggesting is if I have the ability to move, once an arc starts, then it's reasonable to limit the calculation time for instant energy to 2 seconds. And they go on to say, well, you need to consider apply engineering judgment before applying this rule. I have a problem with it because there's second order effects that interfere with other issues, and one of which is coordination. So let me kind of show you what I'm talking about. Frequently, people send me copies of one-line diagrams, one-line projects, and here's one in particular that was sent in. And as you can see, with the current version of EasyPower, we can see from accessing the tool icon here at the top under options what the analysis is set up for. So in this particular case under arc flash, it's set up originally under the old standard 2002, include domain. They put 2-second limits, calculation limits across all voltage ranges, and they're using momentary current. Well, what this has done, if we look at the distribution of the results, what this has done is has the following effect. So here's a bus. If I go into short circuit focus, fault this bus, this is a 240 volt bus, I get a 32 calorie exposure even with the 2-second limit. It's like, that's dangerous in anybody's book. What's going on? Well, if I look at my arranged for arc flash display, I see that I have a bus fault current that's relatively dangerous, branch fault current, and still I'm limiting the time to 2 seconds. What's right about this picture? And the following question is, what's a protective device involved? Well, according to this, it should be sub B5, which is a breaker up here on the main bus. So the next step I would do would say, well, does the change to the new standard affect this result? So let's kind of go back to my short circuit arc flash setup. Let's select 2018. Let's exclude the main. Let's go ahead and leave the 2-second limit in there for now. Let's use the integrated method. Let's apply the results and see what happens. Now when I come back to this, my results went down. They improved slightly, but it's still indicating a dangerous level of incident energy. So this backs the question up, what's the trip device doing? Why isn't this being protected by the system? So if I spread out a little bit and go to coordination, select the breaker and a couple cables and this outdoor weld panel and plot the TCC, it becomes apparent what's going on. And that is, if I have a fault on this bus, my short circuit current does indeed trip the breaker that's upstream. But that's on a bolted fault current. What happens if I have an arcing fault? Well, to see the arcing current, I hover over the plot for the breaker for the device that's tripping, and I right-click and insert arcing. Now, it can't give me an answer. I don't know if you read that result. If I insert the arcing tick mark, it says it can't calculate the arcing current for this device. And the reason for that is we're tripping on a fixed time. The device itself is not controlling the time. So let's go back and fix it. Let's close this. Let's not worry about saving changes just yet. Go to short circuit, setup. Let's take the 2 seconds out of the equation by extending the time, and then go back and plot the same portion of our one line. Again, if I fault this bus, I can see the breaker is being tripped at a relatively quick time. But if I look to see what my arcing current is now, it falls to the left-hand side because it's a reduced arcing current as dictated by the standard is a more conservative result. And it takes it almost 20 plus seconds. So that's why to artificially limit it to 2 seconds was negating the fact that this is miscoordinated. So if I left click and drag, let's look at my instant energy over here. 127 calories the way things are set up. If I readjust my breaker so that that arcing current falls in the instantaneous band of the breaker, now I get a half calorie exposure, which is, and so my problem is because we were having artificially limiting the time to 2 seconds, we obscured the fact that this is miscoordinated. It really wasn't all that obscured because we still had high instant energy and something should have rung a bell. So again, if you're going to use the 2 second rule, which is limiting calculation time to 2 seconds, do it after you've done coordination because you don't want to obscure what's going on. Let's kind of go back to my presentation. So the fact is, we used to say the 2 second rule is not a rule because it was in the annex. Now it's been moved to the body of the standard. So, okay, let's admit it's a rule. In the standard, it says it can, they imply that the rule, if you will, the 2 second limit can be applied across all voltages. I guess I would discourage the use of the 2 second rule above 240 volts because in the 480 volt range, you're talking not only potential for obscuring the coordination issue, but actually having results that could hurt people that were slow getting out of the way. So that's a 2 second rule. So let's get back to the impact on the changes in the standard. The new standard may mean dozens of additional panels that need to be added, and the cost impact could include an increase in data collection time, a more complex model, and for sure more labels. So what are our options? Well, the 2 second limit is now a rule, so it can be applied to some of these loads, and assuming that nothing else goes awry, it would give us a relatively quick result, but we're still have to collect data to understand when to apply it. So the alternatives may not be covered by the standard, but even the application of the rule should involve sound engineering judgment. Back in 2012, in the NESC standard released at the time, which is the National Electrical Safety Code, a study was referenced that had been conducted by two large utility companies where they went through and surveyed all the equipment and categorized by calorie range the maximum calorie for that particular equipment and voltage. And so in table 410.1 of NESC 2812 version, they have this, and I've kind of rearranged it because this table 410.2 includes higher voltages and 410.3 includes very high voltages. The point I'm trying to make is, rather than doing a calculation based upon this as the standard that I'm following, I could make a case that if I have panel boards, either single phase or three phase, or even open air buses and pad mounted transformers, all these could be rated at 4 calories without having to do the calculation, as long as I know it's in the 50 to 250 volt range. And so what that means, and an outcome as far as the client is concerned, is if I set my daily wear minimum to that level, say 4 calories or 8 calories, I have the justification for using a generic arc flash label on those elements, and I may or may not need to do data collection. Again, that's not a given, that's just one potential. But it is based on sound data and a recognized standard in the industry. So you'd want to make sure you document the justification. So that's option 2. Now, I mentioned there was additional testing on arc duration, and here's just an example of the typical results, and that is on low voltage, and again, this is 250 volts or less, that arc could be established, but it would not self-sustain with available fault current less than 4 kiloamps. And so the 2-second limitation is fairly conservative. And if I have any situations where I have this voltage and this current, there's a potential that my max calculation time could be set at less than 2 seconds. For instance, 1 second, and still have 100% guard band on what my instant energy is. Now, this doesn't eliminate the need to do data collection, but it could have some impact on what my decisions about daily wear and hot work, and again, what my bandwidth is as far as personnel and maintenance crew. So what I'm trying to say here is the client may have some particular needs or direction that any one of these options could impact, and it's I think helpful to be able to inform them and discuss the trade-offs involved, because there are a lot of panels, and if the data needs to be collected one time just for completeness of the one line, that's all well and good, but it may or may not necessarily require a second visit to apply a label. In other words, we could apply the label knowing that it falls into a category and that's covered by this particular standard. Now, that's just 3 different options that don't cover the whole possibility of a range of possibilities. What I am encouraging you to do is talk to your client and talk about the trade-offs involved, because that's where the rubber meets the road. And if they're trying to keep up with the changes in the standards, there's some concern about tracking single phase and DC for that matter. And for what it's worth, EasyPower has the ability to do both. In DC, we use the max power method, which is, again, generally accepted to be the way to do DC arc flash. And for single phase, we calculate the single phase current and then use the 1584 model to calculate instant energy. Both of those methods are considered to be conservative, and use them accordingly. Use those options in the tools accordingly. So that covered what I wanted to discuss. There were a couple questions. Okay, Luis is saying he's been observing in the IEEE documents the arc duration time and opening time would be explained. So the arc duration time is a combination of so in the case of a breaker or a switch that's being triggered by a relay, the opening time includes the relay response time plus the opening time of the breaker. In a solid state low voltage power circuit breaker, that trip unit is included in the TCC curves that the manufacturer releases. And so you have a width of the curve that gives us some variation in time. And the left-hand side is when the curve is sensed by the current is sensed by the device. And the right-hand side of the TCC curve is the quote-unquote manufacturer's guaranteed opening time, as long as we're using it in the voltage or the current range that it's been tested. So opening includes both the response time and the opening time of the breaker. It's different at low voltage versus high voltage because the switches or the breakers can have some significantly long opening times. Luis is saying the NESC table is limited to 208 volts to 1,000 kilovolts. 5.5% Z serves from a 500 milliamp system, 500 MVA system, which should be considered and evaluated. Again, and that's a good point. They give us those details of what the standard was, and if my system exceeds those limits that they've made the testing on, then maybe that's not a good solution for an operation. In fact, most of that was done in the utility company where those limits are exceeding what most industrial operations have to deal with. So that should be part of the discussion. And I appreciate the question because it's exactly my point. I think presenting to the client what the options are and what the basis for the trade-offs are is the value that you bring to the table. Good points raised. Not necessarily a panacea or something that is the right answer for everyone, but it's, I think, where the value of an engineering expert is very useful, especially if the client can trust the conversation. Thank you for attending today. By all means, check out the website. We have new arc flash workshops scheduled and online regional training, and all this is in the newsletter. So make sure you open it up when you get it. Have a good day.